Okay, so in this video we are going to look at the reverse engineering slicing options. Um, I've been given a file from an actual customer that we're going to use for this. I'm going to go ahead and load it, and I know this is a very large file, so I'm going to speed through the loading process. Okay, so we accelerated that a little bit. This took about 2 minutes to import. We can see there's a total of right around 2 million features or facets. For reference, the application is consuming on the order of 5 to 6 gigabytes of RAM during this process, so keep that in mind. If you don't have that much available, the application will consume a relatively large amount of RAM for that process. So having imported this file, I'm actually not quite sure what this is. This looks like a 3D scanned cap of some kind. There's clearly something on the inside that wasn't scanned as during the process, but that's probably fine. If we turn on the edge display mode, so we use the keyboard shortcut Alt and E, we can see there's a lot of triangles, and some areas seem to have small amount of detail that hasn't been fully resolved, and some are more in detail. I can't comment to where that came from or what the purpose is there, but generally know that this much data does work. So you can see, 2 million facets is fine. It does take a little longer. There are a lot of processes that go in the background that you don't necessarily see. What I'm going to do for this video is I'm actually going to reduce this down. So the 2 million facets are fine. For the reverse engineering that we're going to do, where we want to take slice data through this, that much facets aren't necessarily needed. It's probably best to start with a low resolution model and then work up to more detailed if the results show that more detail is needed. So what I can do, first of all, I'm going to turn off the edge mode. The few things you show it often makes it a little bit faster, but I'm going to switch over to the bodies tab, and this is one of the reasons why you want to keep as few facets as necessary. Anytime you make a switch, the application goes in and it double checks what's being done between one step and the next. So we're now in the bodies tab, and I'm going to go ahead and I'm going to simplify that body down to an absolute number. And for the purpose of this demonstration, I'm just going to go with 100,000. So like I said, right now we're at 2 million. So we're taking this down to 5% of the original size, so 1/20th approximately. Always I recommend you do the preview. This will take a minute again. And then once the preview completes, we can scroll around this, kind of take a closer look at what the result looks like. We can turn on the edge mode, and here we see we have more uniform triangles. These aren't we have more uniform triangles, and these aren't necessarily made to change their shape to be better or more uniform based on their angles, but this is a reduction in overall count. We could have also used the remesh and just try to get to a lower count by setting the triangles larger, but this is the more efficient process. Generally this looks fine. Again, if I had a specific use of the data in mind, I may or may not choose to do that. I may go larger or smaller. Again, that very much depends on what the data is intended for, but we're going to go ahead and we're going to apply that, which will turn the preview into the actual data, and that will also come with a reduction in overall memory consumed and so on. So once that completes, we are left with the new body. We're going to cancel it, or we're going to close out of that option. That alone triggers an update again. And what I'm going to do first, I'm going to go to export, and I'm going to save this as an STL file. The original file is still here. I'm not going to overwrite that, but I'm going to just give it a name that makes sense to me in case I need to come back. You can pick between ASCII formatted or binary formatted. ASCII means it's a human readable format that will explicitly call out facet locations in a human readable text file, basically. The binary is way more compact, also a lot faster, just because it's so much smaller. So I always recommend using binary unless you have a specific reason why you need to use an ASCII file. Some applications, if you export to an STL file, some older applications still need ASCII formats because of how they're written. But just saving it, you can write as a binary. It's very quick. Now we have this as a backup option. We could go back in, load it, and then use it directly, or we can just continue from this. I always recommend with bigger steps like this, it'll save you several minutes of time if you have to come back due to some other issue. Okay, let's take a look at the reverse engineering tab. Slicing has really only got these two buttons. The slicing button actually brings up its own tool set. We do have a few settings that are specific to this. I briefly want to explain these. We have clear on new import. It is somewhat self-explanatory. Means if you bring in a new file, it'll delete all your slices that you've previously created. And with that, I mean actually the planes, not necessarily the data. Delete upon conversion. So if you go ahead and you convert it, which doesn't really apply as much anymore now, but it would also delete them. Rotate DXF, that's one that maybe needs some explanation. If you turn this off, the DXF file will try and generate planar data that is where it's located in the model. So it won't lay it flat into the XY plane. It'll keep XYZ coordinates in place, and a lot of applications can't actually use the Z coordinate or the Z coordinate. Because it doesn't know how to interpret that in terms of a line drawing. Some applications can and some cannot. Usually if you try and bring it in as a sketch, then you'll need to have it rotate and lay it flat into the XY plane. And keeping this on will do that. If you have multiple slices and you keep save layers as files, it'll create one file per slice. Otherwise, it'll just lay them all together into the same plane. So if you have rotate on and this off, it may end up being that you have a lot of data that just overlaps. The minimal content is kind of a special feature. For DXF files, there's a lot of header information that's often generated as part of that file output. If you turn on minimal content, it will only create the actual geometry data. It won't include headers and things like that. Most applications expect that. Some applications are fine if you leave that turned off. I would generally leave this turned off because you'll get a more consistent file output in that case. As far as the DXF itself, arc center distance tolerance, arc minimum segments, these apply to the convert to arcs option. If you turn this on, the application will try and create arcs where certain conditions are met, specifically the tolerance and the number of segments. So it would try and find 4 segments that approximate an arc with a center tolerance of 0.05. Generally, yeah, you can turn that on if you want to use that. That's fine. Generally, I recommend you keep this off. That way the application will just output straight segments, and then you can use your CAD application as a way to create a better fitting arc through that. The reason for this has to do with parameters that you may want to carry over, or the application may find things that you just inherently don't think should be an arc. It may look like one, but it's actually not. It may be part of a chamfer or something like that. And the same with merge straight lines. It will try and combine multiple lines into one if their angle tolerance is below this number here. and then also distance tolerance, so the overall deviation from that straight line can be defined with this value. Again, I recommend you keep those two off and work as much as possible in the CAD application that this is going to go into. If you have certain needs for those, you can turn those on, obviously. Output digits, generally keep that to about 6. If you add a lot more, you're actually not going to get a lot more data, just because the intersections are all defined as a single precision floating point number, where 6 digits is generally on the order of what you're going to get out of that. So again, leaving these set to their defaults is generally a good idea. Lastly, down here with the surfacing, this applies if you're trying to generate a surface plane as opposed to an intersection curve. And we'll cover that real brief. When we create an intersection curve, the export option will allow us to save those as an STP or a step file, in which case the plane is not being laid flat, it is being provided to a CAD application as just a planar surface. For those cases, we do want to use exterior trimming. That doesn't actually apply to all the algorithms, but we generally want to keep that on. If we use that approach, we have several methods by which the intersection curves can be turned back into a surface, and we got the triangulate, tessellate, Delaunay, and an offset of the Delaunay. So it won't create just the Delaunay triangulation. It'll try and essentially create an offset from the perimeter, and then within that create a Delaunay. These are sort of hit and miss. Sometimes one will work, sometimes another will work better. I recommend you try one, see if that works, and if not, go back. That's where some of these save steps come in as a very useful tool. But again, try and keep this to the default unless you have specific reasons why you want to change that. Alright, let's take a look at the actual slicing for this. So you click the slice button, and that brings up the slicing dialog. Initially, not too much going on. You have this option here, which is add a new slice. That's generally what you're going to be doing the most. You can go in and edit a slice, delete a slice. You can import a slice. So if you create a plane, you say, yeah, this is the one I want to use, you may want to go ahead and save that so you can bring it in later again. And this is the button to save a slice to a file. The other option here is to define parallel or rotated planes. We'll cover that real quick to see what these do. It pretty much does what you'd expect. You create one plane, and then you can either create a rotated version of that or a parallel offset if you want to put a lot of slices through this body. So let's start with one slice here. I'm going to click the Add New Slice, and it's going to ask me how I want to define the plane for this slice. Now, this body very much looks like it's rotationally symmetric around an axis that goes through this section here. So if I look at my options, the existing face is just what it means. You can say, okay, I want to use one of these faces. So you click on this and it gives you a preview. You can pick one and it'll create a simple plane through that. And that's probably not what we want to do here because we don't have anything that is clearly aligned with that. So let's take a look at the other ones. We've got parallel, which is defined through a point and a surface. What's meant with that is you define a point, and you say, okay, the plane has to go through that point, but you want it to be parallel to some other surface. And that is similar with the normal definition, where you say, okay, you have a point, again, the plane has to pass through that point, but it's normal to a line. So it uses the line as the normal vector for that plane. And the normal vector, for anyone that's not familiar with that, is just it's a direction that points perpendicular out of the plane. 3 points is quite self-explanatory. You define the plane through 3 points, and the plane will always go through those 3 points. 2 lines is somewhat self-explanatory. You define 2 lines, but if the lines don't actually meet in a single point, then there will be a projection of one line onto the other that defines a central point within that plane, and then it uses the other two lines as directions which shall define that plane. So be careful if you pick this and you don't have lines that actually intersect in a point. Coefficients, so if you have you have the equation given here, ax plus by plus cz plus d equals 0, you can define a, b, c, and d to define that actual plane. That's maybe more on a mathematical level, but it's there if you want to use that. We've got an angle, so you can pick two surfaces and then the angle between them. We've also got from file, and you import a file with a number of points, and it'll put the best fitting plane through those points. So that plane will generally have the least error relative to all the points, and it'll go through the centroid of those points, or the average, I should say, of those points. For this example here, one of the first two makes most sense, or I should say the parallel, the normal. I'm going to use parallel because then we can use the coordinate axes as a way to, or the coordinate planes as a way to define the plane, but we still have to define a point. Okay, so selecting this, we get the option again, point surface, and by the way, across the application uniformly we have the simple picker, which just shows us a point within the actual viewer. You can see the little pink point, it just snaps to whatever's the closest point. Or we've got the more advanced option for that point. So we click on this and that brings up our point selector dialog. Here again we have a number of options. From coordinates, you can type in the x, y, z coordinates, or we can pick an existing vertex, which is really what this would do anyway. But again, it's here for completeness. We can go through there, or we can turn off the snap option, and then if you can see this, we've got a blue point, which is just the projection of the mouse cursor onto the surface, so it doesn't have to be an exact point. So that's where this option is a little different from this. But if we have snap on, it'll just try and snap to one of those locations. Arc center, you think this is the right option to use here, and you say, okay, let's find an arc. The way the scan data works, it sort of rounds these edges, so you don't have a clean arc, because what it needs is it needs at least two edges, sometimes more than that, but it needs at least two edges, and it'll try and interpolate an arc through those. If we bring in data that's very cleanly defined, so it's something from another CAD application, not from scan data, we can often use that quite successfully to define an arc. Here that's not going to work, unfortunately. That would have been nice, but unfortunately that's not the option to choose. Let's go down. We got between points, so we could say, okay, there's a point here, there's a point here, and then it'll be a parameter value between those two. So this parameter can be 0, in which case it's on the end of the first point, or 1, in which case it's exactly in the second point, or any value in between, or even outside of that, so you can go positive or negative beyond that. Again, that's not going to work very well. It's not going to give us a good section here. Let's go on edge parameter. Is the same as between points, but we pick an edge and then we select the parameter along that line. And again, it can go past the end on either section. We got a surface parameter. So essentially these are U and V parameter, or technically there would be S and T parameters, but we could pick a point plane and then define within that plane parameters. That is not going to be a good choice here either. We can do surface projection, which is you pick a point, you pick a surface, and you can say, how close to that surface is it? 0 mean it's exactly on the surface. Edge surface intersection, somewhat self-explanatory. We pick an edge and we pick a surface, and where that edge passes through that plane, that would be that point. We don't have that here either. Next down is a flood selection. That's actually a new tool within the 3.1 application, so you won't find that in 3.0. And that's the one that's most appropriate for a situation like that. And that's the reason why it was developed in the first place. And this is a little bit more complicated, so I want to explain this. Flood selection, what it does is, just like we've seen in the edit section, you start with a surface facet and you let it grow in selection from that starting point up to a given angle. So 10 degrees is probably good. Let's start with 5, and what I'm going to do is I'm going to pick a surface here, and it'll take a second and it'll pick anything that's within 5 degree edge to edge growth from that. So we see this actually not good enough. We'll go in, we'll change that to 10, hit tab, and now we get a pretty good selection of surfaces along this section here. That's fine. Um, what you see is actually the preview point here, and I'll explain that in a little bit more detail. But what I want to show is we can expand this selection and we can start picking more data points. And that's where this add comes in. If we turn this on, our next selection will maintain what we've already selected, but it allows us to pick a second source facet. So we click this one here, and now you can see these are actually not connected, but we have two facets, and it grows up to an edge angle limit of 10 degrees from both. And if we want to, we can keep doing this. Note that if you want to clear it, the only way of doing that is turn the add off and pick another source. So we're going to keep going. We set selection up there, and that's probably about as good as we want to get it. Okay, so we have a bunch of source facets, and we have a type selector here. And type selector is cylinder, cone, or sphere. Those are the only ones that really make sense in this scenario. What we are getting is a best fit cylinder that passes through these facets. And the average height of that cylinder is where this preview point is being placed. And we get an error. This is the maximum error. So 0.16 or 1.6 times 10 to the minus 1 is the distance between any one point and that center. And when I say any one point, the largest distance out of all of these is this value. Okay. The other thing we see if we zoom in here really close to this preview point is we've got the X, Y, just like here, red, green, blue, X, Y, Z, or Z. We've got also this light blue line, and the light blue line indicates the axis of a cylinder. It would be the same if we went with cone. So it indicates the estimated axis of that object. If for some reason we pick a bunch of surfaces and it goes exactly, perpendicular or any other angle than we expect, it means that the data is probably not good enough for our purposes. That can be the case if we have a very subtle curve to the sides here, for example. So these seem to be pretty well aligned with the overall axis of this. But if it wasn't, then we probably see this axis go off at an angle. Generally, this is a relatively good fit from my perspective. And again, more work on this would probably tell you exactly where that point should be. But as far as the imported data, this is as good as you're going to get. The other option we have is to actually use the measure tool that we've seen in previous videos and get a number of data point samples and then use that as a way to get an idea of where that point should be, and then we could just type it in. But for this case, this is probably the option to use, and we can apply it to the other surfaces as well. We can uncheck this and start selecting down here or on the side to get a different center point. Then we can compare those numbers. But for this case, I'm just going to go ahead. I'm going to say OK. That's the point we want to use. Now we're back in the plane setting. We've picked that point, which is the PX point XYZ. These are the coordinates here. The other thing we still have to do is pick the normal, the direction. And we can either go in and just say, for example, y direction. We can type this as as 1, and then make this 0, and that'll give us that normal vector. Or we can pick a coordinate surface, so we can say xy, which is the original one we had, yz, and again we see down here in this little triad the orientation of those planes. In this case, it looks like this plane is not intersecting any of these features on the side, so this may be a good one to use. I'm going to go ahead and say OK once I'm happy with this. As a reference, the slice preview is just a graphics card related sort of a quick preview to see what it might look like. You get sort of an internal view in there. That's nothing more than a preview, and it's just it uses the graphic card algorithms to get that, so don't rely on that too much. But once we're happy with this, we can click OK, and then this will take a second. Okay, the application will generate those intersection curves, and initially we don't see too much, so we're going to turn off the edge mode again, Alt and E, and now we're also going to turn off facets with Alt and F. And now we can actually see the intersection lines that are being created here. And that's pretty much all there is to creating these slices. So with that, let's leave that as is. So we're going to close out of this. And once we do that, we see a lot of stuff go away because we are now in a slicing mode. So we don't have access to the other things anymore. The application wouldn't know what to do with that. Switching over to the Export tab, we see that our facet representation and our boundary representations, those are not the options for export, but we have options under the slice section. So we have DXF and STP, and the STP, that's just a step file, that's the short version of a step. But what it does, it generates facets from those sections. And like I said before, it's probably not the best way of doing that, but it is there, and I gotta admit, it is hit and miss. Sometimes it works, sometimes it doesn't. Some CAD applications have no problem bringing in a step file that's just a set of planar facets in space. Others say, hey, I couldn't find anything, there's nothing there. So understand that using that may or may not work in your specific application. DXF is quite a robust method. So we're going to go ahead and we're just going to call this its default name. I'm going to do save, and then I want to show you what that looks like, and for this I'm going to use a Libre. So in a Libre you can just import this as a DXF file. It's quite tolerant of that. You have to play around with the units like we've previously mentioned. DXF STL files don't carry unit data, so you probably want to stick to what you've used if that works. Otherwise, you may have to scale it. Applications like Libre are quite capable of doing that. Visible layers, maintain projection, that's all fine. Once you load it in and the application process it, it will bring it in as a drawing file, because that's the only way a Libre understands what a DXF file is. And we can very much see this if I go back here and turn this back on. You can see this as it's being rotated, and the direction of rotation is a little bit ambiguous. So it's rotated to whichever one is closest, but the data is there. Okay. Initially this looks like there's not much you can do with it, but it's actually not the case. You can activate the sketch, and now you have the underlying edges directly available here. Now what I said earlier about the arc being recognized, there's a good chance that it would have put in an arc here, but it may be that it's not an exact fit. So I always recommend you manually recreate those arcs if that's what you want to do. And most CAD applications will have their own way of doing that. You can have an arc, start, end radius, tangent arc, things like that. I'm not going to spend too much time explaining all that, but that's definitely a feature there. And if you do that, you also have the benefit of having it parametrically as opposed to just bringing in as a set of unparameterized features. So this is what you can do, and if you happen to use the Libre for these kind of things, other applications are very similar as well from my experience. You can often just take this and then copy paste it into a sketch. So in this case, once you're actually inside the sketch, you can do a Control A that selects all, and then you could do a Control C to copy it, go into the CAD side of it. So this is essentially the drawing side. Go into the mechanical CAD side of it and paste it on whatever surface you want to use it in. Maybe recreate where this axis passes through, because like you can see, some of these are not very clear. So you may want to use, halfway between this side and this side, create an axis, and then pick whichever side is better, rotate around that axis to generate your original body again. That's generally the best way I can recommend doing these kind of things. Okay. Now, back in here, we could turn our features back or facets back on with Alt F. Let's take a look at the import export of this thing here. So if we wanted to save this plane, we can go in here and click on the save slice, and just call this slice 1. This is being saved as an InStep slice file. This is not a specifically associated file format, but it's just one that doesn't conflict with anything, or shouldn't conflict with anything else. It just saves it. It's it's a very small file. It doesn't take up much space. So if you went in and we deleted this, and they go, oh, oops, that's not what I wanted, you can go back and re-import this slice. And importing the slice will recreate the intersection curves. So it's not, the slice file itself does not actually contain these. So you'd have the option of, and this may be something I should mention as a recommendation here, is if you're working with a body like this, you may want to defeature it down to a level that's easy to work with, just like we did now. Save this slice definition, go back, import the original, and then just import the slice definition, which will then apply the intersection of the plane with that high definition body. So yes, it'll take longer to create that slice again, or to create the intersection curve, but we're not spending as much time with the, finding the center point, finding the plane, things like that. Okay, so that's kind of a quick tip to make that process quicker. This is a tool I use a lot. It doesn't always work 100%. Sometimes you have to go in, just like I showed in a Libre, for example, and sort of make a best guess as where those curves go through. Okay. Like I said, we can also directly double click this and say edit that, I should say, and then we can go in here and we can change our our definition of that if that's something you want to do. So in terms of offset and rotated planes, which is accessed through this option, I generally recommend that you save things first and then you process through that. Just a lot of stuff can go wrong in this process, but let's say we wanted to do a rotated plane and we have our original slice here. We go in and we define an axis, and we have all the standard options for a line which defines our axis point. But I happen to know that the center point was right at around 33, so I'm just going to use that as a quick way of showing this. The axis does not have to be unit length, so this is a length 10, that's perfectly fine. We can define the number of planes that we want to rotate. We can define the axis angle, and that will be interactive in that sense. Once we're happy with that, click OK, and that will go in and actually create those intersection slices, just like it did for the original one. So we have our first, we have our second, we have our third. We can work with that just the same way again. We can right click and we can delete all, yes, and then we can start over if that's what we want to do. It's a very useful way to do this is by saving slice, reloading. It's just like saving the STL file, bringing it back in as a way to prevent any kind of issues that might come in. Parallel is exactly the same as the rotated, that's the default. We can set a distance here, say 5. We can pick as many planes as we want to take. Even if these end up being outside, so you can see this actually extends past the body, there won't be any intersection here, so we'll have, you know, if we take a larger number here, so we'll only end up with these 3 additional ones. This 4th one won't exist if we click OK. So we see these extra 3 that came up. So this is our first one, and then the naming is just based on that. And then just like we did before, we can also save these definitions. So if we, you know, call this slice 4, go in delete all, and then we can load these in just the way we did before, and that will just recreate those intersection planes. And that's about it for the slicing data. Keep in mind that if you have slices, it basically blocks everything else. You can't work with the bodies, anything like that. It's just the reverse engineering slicing stuff. We can go in and either just manually delete these, so we can right click on these and then do a delete all, or we can also just reset back to our facet only representation here, and that opens that back up. It's the same thing. Clicking to triangles is just going in and deleting slicing data again. Okay, in the next tutorial we are going to take a look at the relief data, this section right here.